So we're jumping way ahead in our review here. We've gone from chapter 1.1, which was lines, up to straight up to 2.4, exponential functions. And we'll start off with just the definition. What is an exponential function? It's a function of the form a to the x. Right? So a function f of x is a to the x. And that's what makes it exponential. The x is in the exponent. The variable is in the exponent. What's a? Well, again, a is called the base. And since I want to allow x to take on really all possible values, we want a few things not to happen here. If x is something like 1/2, then that's a square root, right? We're taking the square root of a. Well, square roots of negative numbers aren't defined, so we're going to specify that our base a is always bigger than 0. Alright, so that we don't run into weird issues like that. And also, what happens if it equals 1? If it equals 1, 1 to any power, 1 to the x would always be 1, and that's not very interesting. So we're going to rule that out too. A is bigger than 0 and not equal to 1. But anything else, like 2 to the x or 1/5 to the x, something like that, is called an exponential function. And one thing I think you should know, something that always helps me anytime I deal with functions, is I have this picture in my mind of what the functions look like. So here's the graphs of these functions. Here's case 1, where a is bigger than 1. What's an exponential function do? Well, if x is 0, a to the 0, anything to the 0 is 1, right? So if x is 0, our y value should be 1, so it cuts through right here at 0, 1. And as x gets bigger, again, pretend a is like 2 or something, 2 to the x, as x gets bigger, 2 squared, 2 cubed, 2 to the 4th, 2 to the million, that starts to get very, very, very big, right? So as x gets bigger, this function blows up. It becomes large very, very quickly. And as x goes in the opposite direction, as it becomes negative, well, a to a negative number means 1 over a to that power, right? So this becomes 1 over some huge, huge numbers, and 1 over a huge number is a very, very small number. So this shrinks to 0. It never actually equals 0, right? It's still 1 over some positive number, so it never actually gets to 0, but it still gets very, very, very small. So this is the graph of y equals a to the x when x is positive 1. And I won't talk through this one very much, but if you want to think about it, you can convince yourself of this. The graph of y equals a to the x when x is, when a is bigger than 0 but less than 1, right, the only other allowable case, is a reflection of this graph through the y-axis. So it still cuts through at 1, 0, but now it shrinks to 0 in that direction and blows up to infinity in that direction. So those are the graphs of exponential functions. They're the types of graphs you should have in your head. Really, this is the one I'm usually thinking of because, as you'll see, for reasons, there's only 2 bases we tend to work with most of the time, which are 10, and 10 is not used all that often. The base we tend to use is e, the number e, which is about 2.7 something. So it still falls under this category. And so very quickly, because I know those 2 graphs, now I know graphs of other things. For example, let's say graph y equals 1 over 2 to the x minus 1. Well, in what sense is this an exponential function? I just need to rewrite this. 1 over 2 to the x is actually the same as 1/2 to the x. Right? If you distribute this out, I'd have 1 to the x up top over 2 to the x on the bottom. Well, 1 to the x is still just 1, so I've got 1 up top, and 2 to the x on the bottom, minus 1. So that's really what I'm trying to graph, and you'll notice here, this is an exponential function. Right? This is an exponential function with base 1/2, and all I've done to it is I've subtracted 1. So I'm going to go through this in 2 steps. One is I'm going to graph this exponential function, 1/2 to the x. Well, this is in the second case we just drew, because our base is smaller than 1. Right, so the graph looks roughly like this, 0, 1. there's our graph of y equals 1/2 x, or 1/2 to the x. What is y equals 1/2 to the x minus 1? Well, subtracting 1 from all the y values, if I take all the y values on this graph, and I subtract 1 from them, I'm just shifting it down 1 unit, right? It's a vertical translation. So, take that graph, shift all the points down 1 unit. In particular, if I take the y-intercept and shift it down 1 unit, it's going to go right through the origin. So there's 0, 0. And a sketch of the rest. Something down there, and something like that. So y equals 1/2 to the x minus 1. And I'm not going to say a whole lot about this. Graph translations and rotations and reflections, all that stuff, it pops up very minimally in this course. So I won't say a whole lot about it, but if you do need to remind yourself of how this stuff works, the translations and whatnot, it is, I have it written down here, it's section 2.2, page 69 in particular, talks about translations, etc. Okay, so we'll move on. And what do we want to do in particular? Well, we want to solve exponential equations. Exponential equations. We've talked about linear equations, quadratic equation. What is an exponential equation? It's an equation involving exponential functions. Right? Here's an example. Solve 4 to the x equals 8. Alright, so what power up here, what power of x makes 4 to the x equal to 8? Well, it's not 1. If x is 1, we'd have 4 equals 8, which isn't true. And it's not 2. If it was 2, we'd have 16 equals 8. 4 squared is 16. So it's somewhere between 1 and 2. But what is the actual value? Well, here's what you use to solve exponential equations sometimes. In the very special cases we do in the next few examples, this will be what we use. Typically you go logarithms, though, which will be our next section. But here's the fact that you need to know, which is if a to the x equals a to the y, then x equals y. Again, we're in this case where our base is bigger than 0 and not equal to 1. So if I'm looking at an exponential equation of this form, a to the x equals a to the y, so the bases here are the same, then the exponents must be the same. So what's my goal over here? Well, my goal over here is to use that fact, and the fact requires that the bases are the same. So if I'm going to use it, my goal over here is make bases the same. How am I going to do that? Well, I'm going to realize that 4 is actually a power of 2, right? It's 2 squared, and 8 is also a power of 2. It's 2 cubed. So this is 2 squared to the x equals 2 cubed. And if I just use my properties of exponents now, I will actually have the same basis, right? What does repeated exponentiation mean? Well, it means I need to multiply these together, right? That's how we handle repeated exponentiation. So this is actually 2 to the 2x equals 2 cubed. And our goal is accomplished. Our goal, making the bases the same, is accomplished. Now it's 2 and 2. So same exponential equation, written in a different formula where our bases are the same, and now we can use this fact. If the bases are the same and they equal each other, then the exponents must be the same. So, so the only way these are the same is if 2x equals 3, and that means x has got to be 3/2. So we'll do a few more examples like this. In truth, you can't always do this trick of make the bases the same, right? What if it was 4x equals 9, something like that? It's just not going to work for you, not in a nice way anyway. So in comes the next section of logarithms, but for now we'll do more examples that look a bit like this. Alright, here's our next one. 5x squared plus x equals 1. So I'm going to solve this. Meaning I want the bases to be the same, right? I'm going to try to do this trick again, the exact same trick of trying to make the bases the same. How do I do that? Well, the base over here is 5, the base right now is 1, but 1 is always, it's really a power of any base, right? And it's a power of any base in the following way. 1 is actually 5 to the 0. Mission accomplished, same base. So if these are equal, the only way these can be equal is if the exponents are equal. X squared plus x equals 0. Now I'm solving a quadratic equation. How do I do that? Well, I need the right hand side to equal 0, which is done. And now I'm just going to try to factor. And this actually factors really easily. This factors as x times x plus 1 equals 0. So my solutions are either x equals 0, there's one solution, or x plus 1 equals 0, right? If I've got a product of two things, one of them has got to be 0, x is 0, or x plus 1 is 0, which means x is negative 1. So this equation, this exponential equation, actually has two solutions. Alright, 25 to the x over 2 equals 125 to the x plus 3. Stop the video here. Try this one on your own. Try to solve this exponential equation on your own. And when you come back, I'll solve it. So, going to try to do this trick again. 25 is a power of 5, and 125 is actually also a power of 5. So how about we try to go with that base? Alright, this is 5 squared to the x over 2. 125, that's 5 cubed, equals 5 cubed to the x plus 3. So now if we multiply these exponents together, as we have to do with repeated exponentiation, x over 2 times 2, that's just 5 to the x. And over here, this is 5 to the 3x plus 3 times 3, it's plus 9. Great, same bases, so the exponents must be equal. We must have x equals 3x plus 9. Let's see, we'll solve this as quickly as we can. Minus 2x, subtracting 3x from both sides, minus 2x equals 9. So x is minus 9 halves. And with that, I will say one more thing about exponential functions. Which is the following. Oh, I've left off a crucial word here. As m gets larger. So this expression, 1 plus 1 over m to the m, right? So you can let m be all real numbers, 1, 2, 3, 4, 5, 6, 10, 100, a million. Compute that value for as many counts of m as you want. But as m gets larger, you'll find that this expression actually isn't blowing up. It's not getting larger and larger and larger forever. It's actually getting closer and closer to a fixed value. So it's getting closer and closer to a fixed number, and that number we call It's a very special number. Right behind everyone knows pi, right? Pi is the ratio of the diameter of a circle to its circumference. It's an irrational number. This number here, that this expression gets closer and closer to as m gets larger, is this value e. And again, it's irrational. It's even transcendental, whatever that means. And it's approximately 2.718281828. I don't really have too many places of this memorized. Usually the first 3 decimal places will be fine if you ever have to work with an approximation. So 2.718 is roughly the value of e. Again, if you're working with MyMathLab though and you get an answer, if your exact answer is something like e squared, enter e squared, right? Don't enter 2.1718 squared because that'll be an approximation. E squared is a totally fine answer. Oh, so yeah, so why do I bring this up? Well, for reasons that we'll get into in a few sections. For reasons, e is a really nice number, and it turns out to be the most natural, the nicest base for exponential functions. So, right, our base was a, so it could be anything. Turns out base e is really friendly. So this is why we care about e. And we'll just do a very quick example. So solving another exponential equation, but our base is e now. E to the minus x equals e to the 4th to the x plus 3. Well, here my base is e, here my base is e to the 4th. I want the same base. I can easily get the same base though if I just distribute this 4, right? So this will be e to the minus x equals e to the 4 times x, 4x, plus 4 times 3 is 12. Same base, that means the exponents have to be the same, so minus x equals 4x plus 12. And just solving for x now, subtract 4 from this side, minus 5x equals 12, so x divided by minus 5 is minus 12 fifths. Alright, so the big problem with this, like I said, is if I give you an arbitrary exponential equation, you'll probably not be able to rearrange it so that the bases are the same. Right, so what do you do in that case? Well, you go on to the next section, which is logarithms. So I'll film that now.